All right, how's everybody doing today? Good, that's what I like to hear. So let's get started with the first of the virtual lectures for College Physics 2. Today we'll be discussing electric charge. Many devices operate using electric charge to their advantage, whether it's the lights in your house, phone in your pocket, or even the tablet I'm writing on. All use electric charge as part of their operation. Electric charge was first observed that we have recorded in ancient Greece, where some philosophers observed that if you have a piece of amber and you rub it, you can accumulate charge on it, and then it'll attract bits of things like hay or straw. They didn't know why this was happening at the time, but we now know it's because if you have opposite charges, they attract each other. Charge comes in two flavors. Crap. So it can be positive or negative. If we were to, let's say, draw a hydrogen atom, right, we have our positive proton in the nucleus, and then we have our negative electron in some kind of a orbital around that nucleus. Right here, we're using the Bohr model of the atom just because it works for now. If we were to find the net charge of this, we would see the net charge is 0 or neutral. We can also have maybe an atom that has an extra electron or is missing an electron. Those are called ions. But for the most part, all atoms are neutral, right? And that's why you don't observe everything that has a huge amount of charge. If things weren't neutral, then you'd be constantly getting shocked when you touch stuff because charge would be jumping around to try to get to neutral. Which is what happens where if it's ever like in the winter and the air's kind of dry, maybe you're wearing wool socks, and you touch a doorknob and get shocked, that's a bunch of charge trying to come to ground real quick. And yeah. Okay. And so if we do have our hydrogen atom model in mind, and we want to talk about moving charges, right, as in like a current or whatever, what typically happens is it is the electron that moves, which might kind of make more sense to see if we look at some arbitrarily large atom, right, with a bunch of protons and neutrons all in the center, and then maybe we have a couple electron orbitals. Right, one of these electrons on the edge can kind of hop off slightly easier than it would be to take something from the center and yank it out. Right, that takes a whole lot of energy to do, and you're going to rip apart the nucleus to do that, versus maybe some kind of distant orbital electron that can easily kind of hop off when no one's paying attention. This choice was made by Benjamin Franklin when he first was doing his experiments with electric charge. He decided to make the electron negative, which I think was a terrible decision. But we can discuss my issues with Benjamin Franklin later. So it's important to keep in mind Opposites attract, likes repel. And so if we have two positive charges, we expect the net force to be on each of them pointing away from each other. Similarly, if we had two negative charges, we'd expect them to push against each other. But when we have a positive and a negative charge, we expect them to experience forces that pull them together. And in all of these cases, we expect equal and opposite forces on each particle. Which comes from our good friend Sir Isaac Newton. What a guy. Great hair. And so we can talk about the different types of way materials interact with charge. Right. And so we have materials that charge can flow through easily. Conductors. So a good example of that would be your metals. And so what happens there is you have all your atoms in your material, and then they have what's called free electrons. Which are electrons that aren't fully bound to any atom and can hop around. Well, we'll say not tightly bound. Right, and so these are sometimes called conduction electrons. It's the use of the phrase free electron might be a little iffy here, because some people think of a free electron as one that's under no forces, just moving through space, just is its own thing. But here we're gonna say it's free to move around within a material. So we can also have insulators. Good example of an insulator would be wood. Right? And that's something where all the electrons are very tightly bound. Let's put some little bullet points up in here. We can also have like a semiconductor. Which is where you're somewhere in between the two. And so you could say that electrons can't move around unless you have a significant voltage applied. And when we say significant, we mean a couple of volts. Your standard battery, I think, is a volt and a half, right? And then you have the 9-volt batteries. Car batteries are about 12 volts. And And so these would all be probably more than the typical semiconductor needs in order to knock an electron out. And the idea is if you have something like this, maybe some of these electrons are bound kind of loosely, and then as you add more energy, you can kick it out. But it's not going to just kind of be able to hop from atom to atom at will, like you could with a conductor. And then we're not going to get into this too much, but we can also have superconductors. Right, and so it has all of the same properties of a conductor, but it does it better. And so where you have some resistance in conductors for moving electrons around, in a superconductor, charge can just travel completely freely without any impediment. So the big issue with superconductors that we currently have they all have to be extremely cold in order to operate, which we will get into the temperature effects of like resistance in materials later. But all you need to know as far as superconductors are concerned is, I believe, highest temperature superconductor, I think, is around 93 Kelvin. So it's achievable with liquid nitrogen, but not at room temperature. There's certain things in physics that are known as like the holy grails of physics, right? The kind of things that if you figure out, you just get a Nobel Prize that year. And room temperature superconductors are one of them. The reason for that, right, why are these so interesting, is you don't have heating from resistance. Right, if you've ever touched like an incandescent light bulb that's been on for a while, it gets really hot because of all the current flowing through it and the resistance of the metal itself. And so if there's no heating, you can make them very small. So the current limitations of technology we have, right, like all the little parts in your phone, the reason they can't be made smaller is because they'll burn up if they get too small because they get too hot. And so as superconductors, you don't have to worry about that. And then also we'd be able to transport energy for free, right? And so we'd be able to put a bunch of solar panels in a desert somewhere, enough to power the whole country, the whole world, whatever, and then just move that electricity wherever you need. And so currently the main reason people don't do that, besides like corporate greed and capital, not part of the lecture, is because you do lose energy as you transport it, typically through normal conductors. So let's start talking about the mathematical models for how charge behaves. Specifically, we're going to try to figure out the force between two charges. And so to start, we have Coulomb's law, which as far as we know is flawless. Right, there's a lot of other equations that like, hey, we can use this equation in this circumstance, but then, oh, okay, no. Now if we get to something too small, too big, too fast, whatever, it doesn't work. Coulomb's law works. It's not limited by circumstance. And so we have F is equal to K Q1 Q2 over R squared. And then, since we do have a vector, it's a force, we need to pick a direction as well. And so we pick R hat, right? So it's always going to be radially outwards. Just like when I was drawing how we could have two positives, two negatives, one of each, and showing the forces on those. The force is always pointed from the center of one towards the center of the other or away from, right? And so if we have two charges, it just says the force always points along the line connecting them, right? Which we could see if we were to take a line and go through here, through their centers, right? And so that's all this little R hat is telling us, right? And just like unit vectors of last semester, it has a magnitude of 1 and it points in a direction. So all it really does is give the rest of the equation a direction to point in. I almost asked if anyone had any questions, but that's not how this works. And so the cool thing about Coulomb's law, let me pull it down here so we can deal with it a bit more. It can be attractive or repulsive, and that's going to depend on the relative signs of the Q's, right? If you have both positive or both negative, then you get a positive force. If one's positive and the other's negative, you get a negative force, meaning that it's pointing towards the other object. And so this law here should look very familiar. And so this looks like Newton's law of gravitation, right? Where we have this, right? And so in both cases, we have some constant, and then we have some intrinsic property of the material. We have R squared, and then we have our R hats. Cool. Right, and so the main difference between the two is this is going to be always positive. Cool. And then, yeah, that's that. Okay. And so let's get into current. So current is the flow of charge. All right, so if you have an object like a metal that's a good conductor, and you apply a voltage, which we'll get into next week, is the incentive for charge to flow, then charge will flow through the material, you have a current. If you apply the voltage to an insulator like wood, you don't get a current because it doesn't conduct the charge. And so if we think of a flow of charge, right, we have a bunch of charges all traveling in some direction. We can quantify this by I is dq dt, right? So just like we would have velocity is dx dt, right? The change in position gives you the speed. So here the change in charge gives you the flow. All right, this is going to be an important equation. Okay. And so we can get into the shell theorems a bit. So we talked about these last semester with gravity. And so we have the two shell theorems. So we'll start with your outside the shell. And so, well, yeah, let's start with something called a test charge. So we're going to take some arbitrary positive charge, and we're just going to try to imagine how it would experience the setup we're doing. And so if I have let's say some shell of, we'll say it has a bunch of negative charge distributed across it. Right, so uniformly distributed negative charge. Right, so you can think about if, maybe charge was icing on a cake, and you're going to take it and you're going to cover this sphere with a uniform thin layer of that. Now you have the same amount everywhere, and it's uniformly distributed. And so we can imagine I left a charge. That's a shame. And so if we try to imagine the force experienced by our test charge, you're going to get some amount pulling you up towards the top, some pull down, some pull in the middle. Actually, I'm going to redraw this so it's a little better. So let's try to make sure everything's centered. Then we'll put, that's a terrible color for this. And so we have our negative charges kind of covering that. And so if you think, right, some point up top is going to be pulling up, some point at the bottom is going to be pulling you down. And if you were to take the combined effect of these 2 points you're looking at, what you would get is a net pull straight towards the center, right? So if you add up this vector and this vector, you get something that's going to be pulling you this way, right? And so that same line of reasoning works out everywhere else along this sphere, right? Whether you go into the plane, out of the plane, you can do that. And so effectively, what you get at the end of the day is well, let's say there's some total charge Q built up on this sphere. If you go to the central point, you can just, well, we'll say negative Q. It's a negative charge. You can just say that charge, negative Q, is at that point. Cool. And so I have technology. Haha. Oh, that's fantastic stuff. Right, so if we are outside a conducting shell of uniformly distributed charge, let's say Q, we can treat it like a point charge with the same magnitude. As you can imagine, that's going to make life a lot easier, right? Had I asked you to solve this using Coulomb's law, you would have to go through and find each individual charge along the surface, plug it in with your test charge, and then that would take all day. And so as you can probably imagine, what we're going to go through is the same kind of line of reasoning we did last semester, where you would do the equation for one, the summation for a few, and then we have the integral for a distribution. Right, we have the exact same line of reasoning we're going to go through this semester, right? Sometimes you got to integrate the moose. Okay, and so the next shell theorem is, now let's say you're a point particle inside the shell. I'm going to keep it 2D to maybe simplify things. And so we have some kind of a uniform distribution of charge for a net charge negative Q. And so for this one, what you can say is, right, if you think about the force that pulls you up, force that pulls you down, left, right, your diagonals, right? Sum of the force is 0, right? We saw this last semester, and you should be able to go through and reason this, right? And so it's relatively straightforward when you're centered, right? Once we have it so that you're off center, it is a little less clear, but you get to the same result. With the idea being that, well, here we're kind of symmetric in the middle, so we're not going to deal with the left and rights, right? We're just going to deal with up and down, where we're clearly off center. And so the idea being that you have more charge down here, but it's further away. Up here you have less charge, but it's closer. And so if we look at Coulomb's law again, right, the R is squared, right? So being further away really diminishes the amount of force you experience. And so this is kind of a hand wavy argument. You could, if you want, you can sit there and do the calculus and integrations to prove this, but I would trust the process here. I mean, it's, have a good day, do some calculus. All right, and so the idea being that if you're up in this region here, there's less charge, so the numerator goes down, but it's all closer, so the denominator goes up to compensate. Versus if you're down in the bottom, you have more charge, so the numerator goes up, but you're further away, so the denominator goes down. And so you end up that the sum of the force is 0. And so we'll see that this is all true for forces, for electric fields, for various different things that we're going to see all throughout this section. Which, while we're talking about it, the name for this kind of chunk of this unit is electrostatics. And so we're going to break that up real quick. Electricity or charge, statics, not moving. And so for this semester, or for this chunk of this semester, all of our charges are going to be stationary, and we're just going to see what that does. Right, and so we'll have some problems where you have a handful of charges, and maybe you want to find the force on one of them, right? You would probably know your distances. Right, and you'd be able to go through with Coulomb's law and find that. Right. And so that's a good example of a problem we'll be doing in class. Okay, and there's 2 last tidbits. Charge is quantized. So the fundamental charge is going to be either the electron or the proton, right? One's negative, one's positive, and they both have a magnitude of charge of 1.602 times 10 to the negative 19 coulombs. Right? And so that just the fact that you have this number tells you a couple little interesting tidbits, right? So let's bring this on down here. Oh, I made it purple. That's fun. Right? And so let's think about... What? Okay. Can we stop doing stuff? Okay. And so if we have a 10 to the negative 19, that's a very small number. Right, kind of a strange number to have as your fundamental charge. And so what this kind of tells us is that the units for charge were created before that these were created before the fundamental charges were known. Right? And I guess actually we should call this E because it's the fundamental charge. Right, because had they known roughly the magnitude of charge on an electron or a proton, they wouldn't have picked to have the units be so large, right? So when Coulomb was going through doing experiments with electricity to get all this stuff, he made up a unit that, you know, reflected the amount of charge he was dealing with, which we can see was millions. Right, just tons of electrons, right? To get to 10 to the 19 is a lot. Okay? And so what else? When we say quantized, we mean that it has to come in packages of this amount, right? And so you can have discrete versus quantized. I always like to picture a brick wall when I think of something that's quantized, right? So you got your whole thing, but it can only come in little packages. I'm not going to draw the whole, that'd be outrageous. Right? It can only come in certain amounts, right? You can only add a brick to a brick wall, right? I mean, I'm sure there are more advanced bricklaying techniques that's not true, but we're not getting into that. No. Right, and so for some... Oh, discrete is quantized. So let's get rid of this and put continuous. I think I was going to write discrete versus continuous, but here we are. And so this would be something like drywall, where you just have the whole piece. If you want, you can shave off a chunk. You can make it a little less. You can do whatever. But you also can't see the individual components, right? It's a continuum, right? It can have any value you want, right? If you want, you can cut the top off. You can do whatever, and you're fine. For a brick wall, if you want to start tearing that apart, you have to yank out... What in the... You have to yank out an entire brick, right? And so that's what we mean by discrete or quantized. You can only add charge in increments of electron or proton. Now you can have 2e, you can have 1,000 protons, but where you get issues is if you find something with a charge of like 1.2 electrons. That's not something we're ever going to have in this class. Yeah, and so for most of our applications, when we get into something that has a few Coulomb, that's already, you know, you have 10 to the 19-ish electrons in there. And so this value, right, you are no longer in the regime of quantization. Because if you add 1 electron, then it's 3.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 19. Right? And so with sig figs, it doesn't come into play. And so if you're dealing with something that has small amounts of charge, then you can actually look at the quantization and say how many electrons are in that thing. But once you get up to something that's bigger, then it kind of gets washed out. Okay. And then the other thing we want to talk about is that charge is conserved. And so that means that, let's say we have maybe some kind of a junction in a circuit, and we know that's huge. Let's say we have maybe 2 electrons in this one electron in this. There must be 3 electrons flowing through that junction. And we'll see all of that in practice in class a bit more. Yeah, so that's that.